Greetings to you all. My name is Miguel Sanchez, and my thesis project is called Convection Study of the Red Supergiant Star Betelgeuse, with my director being Benjamin Oprah. At first, I'll give you some background about stellar convection. Due to the nature of stars being agglomeration of light elements, we can model a star as a perfect gas, compressed by gravity and subject to temperature gradients due to an internal energy source that we now know is due to nuclear fusion. In this model, the behavior of the star can be predicted through the equation shown above. The most relevant for these studies is the behavior related to the temperature gradient, which, as we can see, comes in two varieties, one for radiated transport of energy and one for convective transport. This last equation comes as a result of the Schwarzschild disequilibrium condition, where for a certain radius of the star, we, for a certain radius of the star's interior, the temperature gradient is big enough to cause a convection to occur. This inequality becomes an equation due to the fact that at higher temperature gradients, the convection starts working, which tends to lower the temperature gradient itself, while below the adiabatic limit, convection ceases and the temperature gradient rises. This limit between the two energy transport regimes is known as the tachocline, and it determines the thickness of the convecting zone of stars. Being that all of these equations are dependent on the radius and mass of the stars, we can expect different behaviors for stellar convection for different subjects. As an example, the image shown on the left displays the difference between the convective zones of our Sun and of a red supergiant star, such as Betelgeuse. As we can appreciate, in the case of Betelgeuse, a considerable convective shell occupies most of its stellar structure. Stellar convection cannot be observed directly due to huge distances between stars. The only example of direct observation is that of the Sun, where granules can be distinguished on its photosphere. These granules are nothing more than the top layer of Rayleigh-Bernard convection cells, which transport hot material from the star's interior, cooling it through radiation, and then returning it through the intergranular lanes, the dark bands surrounding the granules. The images shown above are a result of computer modeling for three different stars, where the subduction of cold material can be appreciated for each of them. On the lower side, we can see a simulation of what we might expect Betelgeuse to look like, where its granules occupy a large percentage of its photosphere. On the left, an image of the Sun's photosphere is shown for comparison. We are not actually limited to numerical simulation in order to observe stellar convection, and here's when we introduce the granulation signs. The granulation signs describe different signatures of stellar convection that can be found in the stellar spectrum. So far, there are three, and they are the ones observed on screen. The first of them is the widening of the absorption curve, above what we could expect for a normal Doppler shift due to atmospheric turbulence. The second is the asymmetry of these wide curves, which can be seen as a shift in the core and wings of the curve. The last sign only comes apparent once we have compiled the absorption lines in an absolute velocity scale, so each point of the curve represents the velocity shift of the core of each line independently of its position on the spectrum. The image shown corresponds to the third granulation sign done on Arcturus, Alpha Boötis. The scaling factor is not relevant for this study, but for the curious ones, it represents a measure of the velocity fields of the star convection relative to the velocity field that you might expect for the convection on the Sun. These three signs are enough to determine most of the information relevant to the convection of the subject star. Then, the goal of this study is to extract this same information from a real spectrum of Betelgeuse. This spectrum can be seen on the lower right of the screen, which was extracted from the PopStars catalog of the UV spectrograph of the ESO, from 4,000 to 7,000 angstroms, so we could extract the lines in the visible range. In order to identify possible subjects, an artificial spectrum was requested from the Vienna Atomic Line database for a cool giant star. A little piece of such a spectrum can be seen on screen on the left side, where each dot represents the theoretical core of an absorption line. The depth of each line is actually equal to its highness equal to the highness of the dot on the graphic, where green dots represent elemental lines and the red ones represent molecular lines. The blue dots are molecular lines which depth is below 0.2 on an absolute flux scale, which were considered possible candidates for extraction. As can be appreciated on the screen, 4 clean bands were extracted from the spectrum. 5 additional dirty bands were extracted. Dirty meaning that we have molecular lines with depth, which depth is below 20%. However, they are not shown on screen because they were deemed too mixed up to be processed any further. An example of this can be seen on the right side of the screen, where in the upper part we have a clean spectrum free of any molecular lines, and in the lower part we have a spectrum of elemental lines mixed with the little lines that are actually molecular lines with a depth below 20%. As you can see, the level of mixture is too great to do any further processing of lines. After going through all of the bands, 37 lines were isolated and analyzed. None of the lines were extracted from the 0.2 depth molecular lines due to, as we said before, the great level of mixture between them. In the images shown on the screen, an additional element can be seen for each curve, a bisector, which is nothing more than a line composed of the middle points of the curve at each depth. This tool allows us to observe the symmetries of the curve more directly, and they actually are the best way of carrying with stereoconvection studies. As we can see, there is a clear deviation from the theoretical straight bisector, which is an indicative of the velocity field related to star convection. All of the calculation and plots made for this study were made through algorithms of my own creation done on Python. The images shown on screen correspond to lines extracted directly from the Betelgeuse real data. Going more in depth with this topic, we have to mention the granulation boundary. The astronomer David Gray, an eminence on this topic, after doing this kind of studies for different stars, determined that the shape of the bisectors is related to the effective temperatures of the stars, where cooler stars show a C-shaped, while hotter stars show an inverse C-shaped on their bisectors. An example of this can be seen on the right side of the screen, where a cool star is shown above and a hot star below. The reason behind this relation is still a subject of study today, but scientists are almost certain that it has to do with the granules themselves, where stars with low temperatures and with a thick convective shell as a consequence have a large velocity difference between the material that ascends from the center of the granules, which light is blue shifted, and the material in the intergranular lanes, which light is red shifted because it's moving away from us. The material on the center of these granules is hotter, which translates to brighter and as such dominates the absorption curve. This would explain the shape of the bisectors, for cool stars, where the color of their line is blue shifted, with a long wing stretching to the right side of the spectrum. In the case for hot stars is reversed. Their convective zone doesn't have such a large velocity field, and because of this, there is not much difference between the light ascending and descending in the photosphere. But this still doesn't explain the reverse C-shape of the star. This only explains that the granular velocity field doesn't affect the bisectors. In order to explain this, we have to go a little further and know that these shapes have a deeper meaning, directly related to the third granulation sign. This third granulation sign only comes apparent once we have enough bisectors at our disposal. The images shown on the right of the screen are third granulation signs that correspond for cool stars and hot stars. As can be appreciated, both of them have shallow lines on the blue side, while the deepest ones are redshifted. This behavior is related to two factors, which are optical depth and excitation potential. For material on the deepest part of the convective shell, one can expect a large velocity of motion, which translates to a stronger blue shift of the line. This, combined with the fact that it has much more material to penetrate, explains that weaker lines are more blue shifted than stronger ones, which, by contrast, are produced by material closer to the surface of the star. The difference in slope, as can be seen on the right side, is attributed to the thickness of the convective shell. rising dramatically for hot stars where the temperature drops more rapidly as a function of the radius inside of the convective zone. On the other hand, the excitation potential can be expected to rise inversely to the radius of the star. That is to say that material deeper in the star has much more energy, and as such, we might expect that photons coming from this area are the ones that excite lines with a higher excitation potential. The relations shown above were extracted from the Betelgeuse data, where the blue shift and depth of each line is compared to its excitation potential. Though there is not enough data to determine any quantitative relation, the slope of each plot reflects a qualitative relation, which is all we need to carry on and to know that these factors are indeed responsible for some velocity fields present on the third granulation sign. With these relations, we are confident to say that the third granulation sign is actually a way of determining the expected shape of the bisectors if there were not other velocity fields that could affect its shape, which is not the case for cool stars, where the granulation velocity field of the photosphere dominates the shape of each individual bisector. As we can see, the case of the Sun, the bisectors are too redshifted to even come close to the expected shape, while for Gamma Cygni, which is an F8 star, we can see that each bisector is quite close to the expected bisector form seen from the third granulation sign. For cool stars, as an example, plots are shown here for 3 stars: Arcturus, a K13 star, an unnamed G55 star, and the Sun, which is a G25 star. The shape of the third granulation plots for these 3 is a classical example of what you might expect for cool stars below the granulation boundary. The results extracted from Betelgeuse are the ones shown on the screen. As can be appreciated, there is not a clear shape which can be associated to its third granulation sign. Opposite what we could expect for such a cool star, the individual shapes of the bisectors do not correspond to the normal or the inverse C-shape, showing both configurations in a seemingly random fashion. It is clear that the third granulation plot do not reflect any tendency. The same image shown before can be seen on the left side, where only the core position of each line were left. On the left side of the screen, the results of the same procedures made on Antares and Aldebaran are shown. The similar shape of the plots of the red supergiant stars are indicative of a phenomenon related exclusively to such stars, and allows us to carry onwards with possible explanation for such behavior. As today, we believe that the shape of the bisectors are related to the large size of the photospheric granulation for giant stars, something that David Gray studied in 2010, extracting flux difference between each bisector and the position of the third granulation sign at the same depth. As a result, he came up with the graphic shown on the right side of the screen, where for cooler stars, the difference in flux for each bisector can be attributed to a more dramatic velocity gradient between the center and the boundaries of the granules. The discrepancy of the third granulation sign, we believe, can be associated to material ejected from the star, explaining why the stronger lines are actually so much blue shifted, as the absorption material is projected towards us, producing lines with no optical depth at all, as the light is actually re-emitted outside of the star. So far, the goals of this work has been achieved, so further work will be focused on proving our hypothesis and apply these results to the other 2 red supergiant stars chosen for further comparison, Antares and Aldebaran. Thank you so much for your time, have a great week, and stay safely and cheerfully at home. Ciao.